Hello. Thank you for coming for this presentation. I am Tasos Valsamidis. I am a principal engineer at Kaizen Gaming. I'm a member of the enterprise architecture group where we concern ourselves with the developer experience and the core systems of our company. Let me give you a brief overview of what we will see today and how is it relevant with scaling to 500 concurrent customers. So we will talk about a small intro about our company and what have guided us to having this kind of traffic to our site. We will see how the actor model has helped us scale to those levels. What is the actor model? We will see an example of how to model things with actors and some implementations for various languages. We use .NET, and one of those implementations is Orleans. And we will say why specifically Orleans is suited and it's the preferred way for us to go forward. I was inspired yesterday by those presentations, and instead of showing you some graphs, I will show you some demo, which hopefully will work. So let's go, because we have a lot of things to cover, so I will be cutting some corners. So who we are the company that is operating those two brands, Stichiman and Betano. Our products have a very specific traffic pattern. They tend to go up in terms of concurrent customers, and they have massive peaks surrounding the end of events, like finishing of a big match and stuff like that. This is a small graph that I got from our production systems. You can see massive spikes from 20,000 customers to 400,000 in a matter of a few minutes sometimes. So we had to deal with this kind of scaling that we have to do in very short amount of time. We chose to use and implement the actor pattern for many of our services. And let's see what is an actor model. An actor model is actually a programming model. It is a mathematical model that was conceived in 1973, and it has proliferated through the use of various languages and frameworks to many different implementations. It is particularly suited to concurrent computation, distributed computing, and high performance and throughput applications. It's not a silver bullet, so it won't suit for everything. But if we would like to keep on, a single thing is that if you have an application that has a lot of small components that tend to be isolated from other things, it might be something that you should consider. So what's an actor? An actor is a basic block of concurrent computation. This entails that it is something that has the ability to process something, it has some state, and it has the ability to communicate with other such systems. This is a definition, the formal definition of an actor. We will see some things later. I guess we should concern ourselves with the things that an actor can do. It can send messages to other actors, it can create new actors, and it can, taking a message, it can do something about its state or do other things. It cannot try to change the state of another actor. It can only send a message, and the other actor is responsible of doing whatever he wants. So let us see an example of how we could implement a banking system with actors, trying to find out the various entities that we have. We might come with a similar model such as this. And you might say yourselves, you know what, if it's not an actor and it is a service or a class, or a domain model, what's the difference? Well, actually, there is some difference. And it all comes down to this. Say that, for example, the middle account there was the account that was in the movie where Catherine Zeta-Jones had some small transactions going through billions of accounts and all led to her account. What happens then? What is the concurrency constraints that this thing would have if it was implemented as a service or as a small class or something like that? This is the problem, the kinds of problems that the actor model tries to solve. How does it do that? It has this concept of the asynchronous messaging. So it would send a message, you have to do this. And also, this is the internal state of the actor. So it is something that happens in the state of the actor, which is in memory. It is very fast. And then you can subsequently persist it to your databases on yours to have it. So actually, what we see here for those actors, we imply that there is a messaging component there and some internal state for each one of them. Going forward, there are many known implementations of the actor model. Some of the most known are those three. Erlang is one of the first, and this is embedded inside the language and the runtime that they give. Akka, which was a part of the Scala language, and it has been spun off, and it is now used for everything that is running inside the JVM. And our choice, Orleans, which is implementing the virtual actors pattern, which is a bit different, and we will explain later how. In the same family as those are Elixir, which is built on top of Erlang, Akka.NET, which is the implementation of Akka, but in the .NET world, and Dapper, you might have heard, and many other services in Azure Cloud, which are all based on Orleans. There are also implementations in various different languages, but these are, at least I don't know many of them, so I cannot know if they're good or okay, but it is something that it's out there and you can see if it suits you. So let's go with Microsoft Orleans. It was a Microsoft research project. It came from the research labs and has been adopted heavily inside Microsoft. One of the main selling points of the Orleans is that Hello 4 and Gears of War servers were based in Microsoft Orleans, and there were the first things that were deployed in production for Orleans. Right now, I believe that they have more than 100 services in Azure that have an underlying Orleans cluster below. The difference that they have with the virtual actors is that they have the notion that an actor always exists. I like to think of it as a customer. You know, your customer is there. He's out there. He's not on your site now, but he's out there. So whenever he comes to your site and needs to do something, your system has to know and has to respond to that. If not, you don't need to have computing power for someone who is not on your side. So it handles many things, like automatic activation of those actors. It has a location transparency, so inside the cluster, you never know what your actor might end up to, and there is no need to. And also, the scale out is automatic. It's transparent to the developer. The one thing that they have is that instead of calling them actors, they're calling them grains, and grains are placed in silos. One of the big differentiators for us is that Orleans also provides a runtime. And it is very easy to program against, and I will show you how. Because clustering is offloaded to the runtime, you don't have to manage the clustering. Activation is automatic. Executions are secret threaded by default, so you don't have to worry about concurrency inside your actor. Also, the communication is handled transparently. So inside the cluster, you don't have to know where each actor is, and you don't have to, sorry, worry about exceptions that were raised in the client actor or your actor. It is also handled by the system. You don't have to worry about supervision trees and stuff like that, which is imperative in other implementations. This is all transparent to you as a user. So how did we use that? Almost everything that you see is something that has to handle this kind of traffic, those spikes that we have. New implementations that we have all try to be written in Orleans. A small thing. For example, for the session management, we were able to change the session management and scale it within 3 weeks. So actually, it was from the start of the World Cup until the end, we had a system ready to handle the traffic of the World Cup final. Another benefit that we got is that new contributors need just 1 day to see the code, reason with it, and then just be productive. I had some slides showing you some graphs, but I don't think that they are as useful to our conversation as a small demo, which I will try to show you now. I really do hope that people in the back can read the code. I try to guide you through that. So it's a small application that tries to do one thing. It has a SQLite database, and it gets to update and get data from a single row in this database. It updates a counter and returns the result. We have 2 ways to do that. It's a simple one. If I go and say, so this is the simple implementation. As a result of an HTTP call, you go to the database, update, and bring the result back. There is also the Orleans way, which has the call go through a grain, and this grain does the same thing exactly. So if I scroll a bit, and this is the grain where we said that a grain is an actor, it does exactly the same thing, but we have the Orleans runtime handling things for us. As you can see, the code that we have written, it's exactly the same. The only thing that we had to do was implement a couple of an interface and inherit a class, and also add the Orleans in our application. So let's see. Let's run our application. Okay. Let me reset my database and then just run 100 threads, sending 1,000 requests to the simple endpoint, so HTTP to database. As we can see, we get a performance that is around 80-ish requests per second. Yeah, 72.35. Let's go and do the other one. Much faster. So it's 232. It does exactly the same thing. The difference is that the concurrency in the one case is handled at the database level. So the database has to throttle the connections and try to lock the row and update it one by one. Whereas in the Orleans example, we have this operation being done automatically for us by the Orleans framework, the actor framework. And this lock contention is being done by the application, and the database is free to just update the row without any concurrent issues. So that's it for me. I have some references that you can see. I have also created a small repository for that you can run this yourself. And that's it. Thank you very much. I don't know if there is any question that you would like to ask. Nope. Okay, there is one. Do you have time to answer one question? Okay, thank you.
Hi.
Hello.
I didn't get the last example. In the database, you have the same isolation level between the two examples.
The actual call to the database is update this row, set your counter to +1.
No transaction.
No transaction there. If you,
So this is the difference. It has no transaction, the actor-based way with the
No. The implementation is exactly the same. They are calling the same. They're doing the same thing. So let me see. Both things are calling this. Update T1, set counter is equal to counter +1. Nothing different in there. The thing is that one thing has to make, because we're concurrently calling it many times, the database has to handle 100 concurrent calls or whatever your connection pool is. And the other is, there is only a single request to the database at each point in time. So there is no contention for the single row in the database. This thing is getting handled in the application layer. Adding a transaction there would only create some more overhead for each thing to create the transaction.
Thank you for the presentation. Does this differ from database to database? So maybe Postgres might handle it quicker?
Actually, I only used SQLite because it had few dependencies. It's already embedded as code. We've seen the same thing with SQL Server. I don't think I have seen a benchmark with Postgres, but the problem is similar. And this thing is only a single application. Imagine having 100 different servers trying to access the same row at the same time and update it. Because right now we have only one row, try to imagine this happening to 20,000 rows at one time, or 200,000 rows at one time. This is a problem that scales with a number of concurrent requests being done. So you won't need, for example, to have either an application log. If you have the same call happening from two different servers that don't know with each other, one has to wait for the other and then get the new data to update. So this is being handled by the internal state, for example, in an actor, whereas in other cases, you would have to go to the database and bring the new data back and then do the same thing in another server. Thank you.
Thank you.
Thank you very much.